Good evening. I think we're live now. Welcome everyone, ladies, gentlemen, boys and girls. Thank you for joining us tonight. It gives me great pleasure to introduce our topic and our speaker. That is advantages of optimization-driven design for automotive applications. And Martin Gambling from GRM Consulting has very generously donated his time to speak to us tonight about this. My name's Ryan Titmarsh. I'm chair of the Coventry Automobile panel, and I'll be moderating the Q&A tonight. So please feel free to enter any questions. Please note there is a difference between Q&A and chat. So please enter your questions in the Q&A section. There is a hard stop at 7 p.m. So we'll be stopping the event then. We're going to talk for about 40 minutes and then have 15-20 minutes for questions. So without any further ado, Martin, I will hand over to you.
Wonderful, thanks Ryan. Good evening everybody. It's really delightful to be lecturing this evening in this strange world where I'm sitting in this room and my family are next door in the living room. It's part of the modern world we've all got used to, I think. But thanks for joining us and I hope you're having a good evening. Okay, great. So you should be able to see my screen. Now I've said hello and you can see me sitting in my room. I'll knock the video off and we can focus on the slides. So all being well, you can hear me okay and see my screen. So I will crack on with the presentation. As Rowan mentioned, I'm talking about the advantages of optimization-driven design in the automotive sector. This is me. So my background is I'm the managing director of GRM Consulting. So we're an engineering services and software provider based in the Midlands. We've been around for 17 years and really a core part of our business is optimization and we also work a lot in automotive. So the fit really to talk this evening hopefully is a good one. And my background before starting a business was also working for other CE companies in the area of optimization, and I first began in the Motor Industry Research Association in Nuneaton. So I've lived in that auto world for too many years, I guess. It's 25 years. That's quite a lot. Okay, so this evening I'll go through 4 topics. First of all, what I would describe as optimization-driven design. I'll then discuss the tools that are available, both ours and what else is out there in the market. I think it's important to give you all a good spread of the tools that are there. And then I've cherry-picked 2 particular examples to go through this evening before we'll wrap up with our summary. So if we start off with optimization-driven design, what is it? What do I think it is anyway? So my personal feeling is it's a philosophy of using optimization in the engineering development process here in the aspects of automotive design, rather than considering some of the optimization techniques that are available that are either used just at the start at sort of a concept level or something that's performed at the end of a developed part. So you can say, oh, can I make it a bit better or a bit lighter after I've developed it? The key thing is embracing optimization in the day-to-day activities from early concept through developing architecture, vehicle platforms and components right to the detailed design towards the end. So using these methods, there are a few things we really hope to achieve. I feel we can gain. First of all, it's the meeting multiple requirements and looking at getting the best designs to meet those multiple requirements. That's a real strength of optimization. Often if you think of designing a part, be it a structural problem, you can look at it, think of the loading going on and work out the load paths and have a fairly good idea of the structural layout. But when you have, as you do in automotive applications, dozens of load case requirements, finding that best compromise is where mathematics and optimization algorithms can offer you that bit more. So considering those multiple requirements. Secondly, rather than just purely looking at optimization as something to optimize and give us this best design from a concept and these sort of headline figures, is actually using it as an engineering tool. If you've designed something and it has design issues, it has some problems that you need to resolve, you can use optimization to to identify the best and most efficient solution to those problems. And so, jumping to the last point, you can explore a design's performance and start to look at how key changes in the design will affect the performance metrics that you're driving towards. And when you get it right with optimization, it just saves you time as well. It's nothing more boring than sitting there iterating manually a design. And if you can get a computer program to sit there and iterate for you, make those design changes, monitor responses, and get a better solution, that's freeing you up to do other things, which is always a good thing. And I think in the development pressures of modern automotive design and some of the rapid changes we're seeing in platforms with EVs and so on, that's undoubtedly an important capability. So I'll delve a little bit into the processes and hopefully try and dispel a bit of the black magic that is optimization, because it's sometimes thought of as it's not like engineering normally, it's optimization, it's this magic black box. But ultimately, optimization is doing an awful lot of what you might do yourself. If we think about how we develop designs and we iterate them, we just take a look at this flow here. So in this example, I'm taking FEA, so structural design, but the process applies for any application you're looking at. So here we do an FEA. We look at our performance and we look at our simulation results, review the performance and compare it against our targets, those that we've set ourselves. If it's good enough and we think we're at a fairly effective design for our targets, then we stop. If it's not, we use our experience or some classical calculations of fundamentals, and we then look to revise the design, update it, and reassess. And that's that iterative process that we're doing. And that can be quite time-consuming. There are some strengths to the human brain. We're quite good at dealing with things that we want to. Okay. Good. Now, if we look at optimization as a workflow, the flow itself is almost identical. So in here we've got the FEA, and then we've programmatically told the optimizer what the target is to make as light as you can, for example, or maximize some metric. You've got some targets or constraints we've got to meet. So it will automatically measure those responses, check for the technical term convergence, which is us saying, is that good enough? Stop it if it is, and if not, it's going to calculate sensitivities and perform an optimization. So this step here, the sensitivities and optimization, are basically determining the change of our responses, our goals and constraints, to the changes we're making to the design. And then with that, there are calculations that will go and work out the best combination or what it thinks is for the next iteration. It will update and it will go again. So moving on to how we compare them, you can see the flow is the same really. It's just how we do it. So it's working out when we do an optimization that we give it the right questions to answer, and it's able to get that sensitivity information to be able to perform an optimization. And that's one of the fundamental details of optimization and why, when and how we can use it. I'll delve into that in a little bit more. So why use it? I'll go through this fairly quickly so I don't end up running out of time at the end. But basically, get better designs, do it quicker. Some obvious ones: casting designs for thickness, composites. It's an area we're very heavily involved with in our team here at GRM. Reduce that manual iteration loop, as I've mentioned already. So if you're going to look at the combination of panel gauges on a part, you don't want to sit there iterating them and looking at the results. Let the optimizer do the work for you. Consider those multiple requirements. Minimize part cost, material usage. That's such an important topic in automotive. I think Henry Ford made some comment that if you can take something like 10 grams of metal out, you can save yourself a penny on each vehicle, and that totals up to millions very, very quickly. So small gains make a huge difference. And then also you can use the tools to iterate to a point of completion various different design concepts, and with those you can then do trade-offs and understand the different designs. So I've plucked this from a presentation that was made by a good friend of mine down at Swansea University, or University of Wales, I should say. And it's a little question for those that say, we don't need optimization, it doesn't work, it's not, we can get to the answer. And so he actually posed a question to his postgrad students with a simple L-shaped structure you see there, fixed at the base with a load on it. And he filled it with the ribs you see on screen there. And he said, which ribs should I keep to get the highest stiffness to weight ratio? So there's apparently 3,896 different permutations you can pick. And he said, just on a bit of paper, draw lines where you think it should be and give us your answer. And so he did that, and these are the results he got. So if we just take a look at the spread on the right, so first of all, we're looking at the number of people that got the various ratios. And you can see there's a very clear mean at around about 3.5 stiffnesses per weight. So it's a nice normalized figure. But you can see that's quite clear. There's a very clear spread below 3 and sort of above 4. And only right up here, we have just one person right at the very highest solution that was achieved. So if we then, in this case, do a topology optimization, you get the solution you see here, and then he interpreted that into these selected ribs you see in the middle, and that gives us a 5.76 stiffness to weight ratio. So take a little look at that. What's really key is the mean of all surveyed students, which was 149, got us around about 3.5, and really the number of people getting that best solution or close to it was really quite small. So it goes to show that if you can get a tool working right, it's going to steer you in the right direction. And I think most listening will realize if you take that and combine it with great engineering brains, that's when you get the maximum benefit. Okay, so enough about why you should do it and the whole background. What tools are available? So in terms of the types of methods, there are two really major types available we'll go through. First is what's called a gradient based, and these are great because they're fast, they can consider thousands of design changes and just get you to an answer very quickly. And the way they work is this: if we look at our graph here, we've got our design variable change, so that's some parameter in our design. The objective is the performance we're looking at. So it starts at a certain predefined position, and then it calculates the gradient. So that's something it can analytically do inside the solver. When it does that, it moves a little bit at a time, taking the gradient, moving until it finds itself at an optimum solution. And that there is how it works. The next sort of major discipline, and these are the two that you see all the major commercial codes around for, it's a process called design of experiments and response surface approximations. What this is doing is it's saying, well, I've got a design and I can change certain parameters. I don't know inside the maths of the simulation solver what will happen before I make that change to design. So I've got to do some sample points of my simulation model and understand how it changes. So I will change the design variable, run it in a few different positions, and bearing in mind this is expanded out to many design variables. It doesn't make graphing very easy for this kind of example. But when we do it this way, we can then fit what's called a response surface, which is basically an equation that fits through the points and creates an approximation. And when you have that approximate equation, you can easily predict responses at any other permutation of your design variables. So you can really explore, and that's what we'll go through in one of our examples this evening. Okay. Now, there are also some slightly batty and crazy ways as well. There's something called genetic algorithms. Actually, it's a very powerful way, but it's a process of optimization that doesn't really require maths or equations that it's solving. It works on the theory of evolution. It just basically will try 100 sample points, pick the best 10, and then it'll mix the variables from those together and do another 100, and it develops that way. So there are different ways, but they're slightly less commonly used in this industry, and I would certainly consider the top two as the ones that we look at. So in terms of those two methods I've discussed, gradient-based optimizers, what's good, what's bad, and when do we use them? So what's good is they can consider thousands of variables. In fact, nowadays with big solvers, we're up into the certainly into the million design variables for certain problems I've encountered over the last few years. They're very fast, and they achieve that speed because when they have a design change, they don't have to perform another simulation to understand how changing each of the design variables will change the behavior. So that makes them fast. The limitation is there are only certain simulation environments and models where you can get those sensitivities analytically from inside your simulation model. So it only applies to certain applications. Really a strong one is structural, but it also works in terms of internal flow for CFD. And there are several other analytical functions in other codes available that can use it. The most obvious one you see animating on the right, or hopefully you see it animating on the right, is Topology Optimization. It's the tricky name. Is it the same as generative design? I'll let you all discuss that. By all means, ask me questions about it later. Okay, so the other disciplines are DOE and response surfaces. These are great because you can apply them to basically anything you're simulating, and you can bring all the different disciplines you're simulating together. And often the biggest limitation when it comes to automotive design is that bringing all the disciplines together involves bringing all the different departments of a car manufacturer together, and half of those people haven't met each other. So that's something we really found as a bigger limitation than the technology itself. So here we can bring in vehicle dynamics and NVH and all the other factors together. And the way it works, I say, you can just build in these tools nice flows of this is an analysis block, another one, and then extract your responses. And the tools will automatically then go and run a sequence of simulations, varying the design variables and learning about the response behavior. It's something that is very popular in the world at the moment is AI in all developmental. Fundamentally, that's what these processes are doing. They're learning about the response behavior to the changes in our design parameters. And typical applications are vehicle crashworthiness, dynamics, again, CFD and shape changes of designs. And actually, I've been involved in some recent work where we're looking at the overall drive cycle of EVs, so all the different pieces together, and looking at the whole energy management, because you can make a gain in one area thinking that's a great success and you've lost it elsewhere. So it's bringing all that together is the key. Okay. There are limitations to this because we've got to make those simulations and develop a response surface and approximation. We're a bit more limited to how many variables. Gradient based, we can have thousands or more. In these response surface approaches, we're limited more to 5 to 10. You can go a little bit beyond that, but you're into this smaller range of design changes. So you have to be a bit more thoughtful about those parameters that you're considering. Okay, just a bit on the products. This is, I think, the only slide where I talk about Directionally in the whole session. These are the tools that we provide. So our aim as a business is to very much be all things about optimization. We don't do optimization as an add-on to other processes. It's what we exist for. So we've got our tools for ANSYS and Simulia, so for Abacus and for SolidWorks. We've got our core products in Genesis and Odyssey. And then we also have tools for the Siemens platform, so the SimCenter environment. Actually, in terms of the complete structure, we're also adding in some laminate optimization for Abacus in the coming year. But as I say, it's important. It's very easy to just sit here and sell our own wares, and that's not what I want to achieve tonight. I want to make sure you're all aware of optimization, and I want to get you all using optimization. It's a real passion of mine. So these are the sort of other tools that are out there. So Genesis, Odyssey, they are the tools you can see here. But on the gradient-based optimizers, Nastran, so both MSC Nastran and the Siemens SimCenter Nastran have got Solution 200, it's called, which is an optimization solver. There's OptiStruct. DAS themselves have a product called Tosca, which is very powerful, and LS Dyna, which is a traditional vehicle crashworthiness code, has a solver called Task. And what we've seen over the last few years, from our own conference in 2016 to our own conference in 2018, I remember speaking and saying in 2016, integration of topology into CAD tools is where it's going. 2018, nearly every single CAD vendor had added generative design into their products. So you're able to look at concept schemes from some solid volumes inside your CAD package now. The key is always make sure you ask the right question. If you put the wrong boundary conditions, if you ask the wrong question, you'll get a stupid shape. So it's always important to remember, good engineering will give you a good generative design solution, and otherwise they're not. And you see also the same applies for the DOE tools. There's a lot of tools out there that are available, so that it's readily available. It's there. It takes some investment in learning, but it's there, and I can honestly say I've never met anybody that's invested in learning optimization and ever left it again. So hopefully that's a compelling enough argument. Okay, so on to our first example. So this is one looking at some CFD simulation and using the DOE and response surface tools. So I wanted to describe a bit about that. The person that's did the work on this one's actually listening in, or I think he is. I'll see if I get a pling in a minute to see if he's actually listening. Pay attention. So here, what we're going to do is explore and optimize the geometry of a diffuser at the back of this car through CFD simulations. So here's the baseline model. This was actually done all in SolidWorks flow simulation, just the tool that was used for this particular application. And the car started off whereby it had a very open rear end. It's quite a interesting geometry where there's no diff sitting at the back, so we had a very open space to play with in the design. And baseline design had drag of X and downforce of X. So what we wanted to do was see if we could make some improvements in overall downforce through the addition of a diffuser. Now, the people that designed the car had a little go themselves. They went and just did a conservative one, a low angle of 77 degrees and a high angle of 20 degrees. And you can see we've got some good performance. 7 didn't do an awful lot compared to the normal car. Just tidied things up a little bit, and then the aggressive one actually said it would work. But there's more to come on that one in terms of whether it's effective in real life. So what we did is we used the Odyssey DOE tool, and we considered the parameters of the diffuser. So here, this was all managing based upon the CAD geometry inside SolidWorks. There are other ways of moving things in these tools. You can use morphing tools in the CFD solver or in the FE solver. But here we're actually just parametrically controlling the CAD and driving that by the Odyssey DOE tool. So it's got a simple one. Again, it helps to get your head around the whole problems, which is to have 4 particular responses and 4 different variables, I should say. The exit width of the diffuser, the diffuser length, its angle, and the rear ride out of the car. So we're introducing rake into the car. So with these 4 metrics controlling the response. And this is where it gets interesting, and hopefully you'll see, after me talking through this slide, how the processes really allow you to inform and understand the system that you're simulating. So what we've done, we've run permutations. If you can see that on your screen, if your zoom is clear enough, what it's done is for each of our 4 parameters, it's varied them all uniquely and run, in that case it says 27 simulations, and for each of those it's got drag and also it's got downforce, which is just hiding off the screen, as you can see the skulls and stuff. So from those responses, it's built up this response surface, and that response surface allows you to effectively predict any further permutations of those geometry variations. And as well as that, I've plucked out one particular graph just to show you, which is how we can see how the downforce is varying based upon the angle of the diffuser and also the length of the diffuser. And somewhat to be expected, you can see that there is this continual ramping up in both directions, but you can see not just qualitatively but also quantitatively what that response is doing. Now, there's a certain amount to go through in today's talk, and that response surface is of course dependent on what the other two variables are doing at that moment. So if I change the exit width and the rake at the back of the car, then that response surface will then change. And so you find in the tools dynamically you can start to see that, but you can really explore that design. And it's just when you get that first response surface out, it's quite enlightening in terms of understanding your system and seeing what's going on. And so doing this for anything, it could be electronics, could be flow simulation, it could be control systems, aerodynamics, structures, or, as I say, a combination of all of them. And that really is such a powerful way to work. So having got that response surface, it's a relatively easy step then for the tool to perform that optimization. So where's the minimum on that response surface, that multi-dimensional response surface? And in this case, the simulation of a solution was to give us a diffuser of an angle of 12.3 degrees. And you see length 710, width 430, and a ride height of just short of 80 millimeters at the back of the vehicle. So that's what we got. And you can see just a little bit, base car was giving us about 300 newtons of downforce, so it's not a heavy downforce vehicle, just to be clear. The conservative diffuser was good, the aggressive one was good, but actually it wasn't as good as it could be, even though it was a steeper angle than the optimized. You see there was the ability to develop that fine-tuned sweet spot of the dimensions through the optimization, giving us our maximum downforce. And of course, if you change any parameters, it's very easy to go back to that response surface and re-optimize and look at a different solution. Okay, so we'll now move on to my second example, which is applying a process called RDM. I'll explain what it is in a moment, to body-on-white structural design. And this is actually probably one of my favorite processes. It's really, really powerful to use topology optimization to guide a design and do it in such a way that just makes it easy. So you can use the processes in your day-to-day engineering and combine it with your own engineering judgments and developments as you're working. So what is it? It's got a funny name, RDM. I will say it. I was trying to decide whether I would say it today, but when we developed this process, first of all, we decided to call it Magic Custard. And that's because the first versions of the process that we employed, the region that you see there in red was always yellow. Just happened to be the default we were picking, and it just felt like it was forming little blobs of magic custard all over the part to make your part better. So we decided to give it a better name, so it's the reinforcement derivation method, or RDM. What it's really there to do is to develop additional reinforcements and new load paths to something that is existing. So you can see the logic of a developing structure that's not meeting targets. It helps to solve those problems as you design. So it's got a real advantage with those pre-existing structures. And if you adopt this approach, you tend to design something aggressively light to start with, and then let it work through to the best solution. So, and that's certainly how a lot of people have used it. I guess a bit of reason as to why this process has come about, what we would want to use it for, is topology optimization. Hopefully, those of you attending have come across it. It's becoming much more popular with the advent of generative design inside CAD systems. But really, it's starting from a design envelope, a big package volume, setting your requirements for stiffness or vibration or whatever, and then developing the idealized load paths. And that, as you can see, is great. It gives us this scheme for the best layout of a car. But obviously, you don't make cars like that. you make them with pressed parts or extrusions or castings, and trying to make sense of that is quite a leap. And so once you've made your first step of topology and you develop that into a scheme, well, then there's still a lot of work to do and there's details to be refined, and that's where RDM can help. And the other reason is, as a structural engineer myself, the whole ambition that a car is purely designed for structures is a little bit naive. There are so many other requirements, and the EV platforms particularly, there's an awful lot to package, and there's new package layouts to be managing. So there's certain things that can go in certain places, and then the structure has to fit around that. So that's something we need to manage. And also, often in vehicle design, you're not always starting from a clean sheet. You might be having the front end from a certain vehicle, or you're extending a platform. There's development of existing platform architecture, and so working with that and combining with that is a key. So I'll take you through now a little example of its application to a 2002 Ford Fiesta. Nice little car. I sadly say that wasn't my first car. Mine was a Mark II Fiesta, so that's how old I am. But a good little car, and here we've got a nice simulation model available that was provided courtesy of Bolton University, Bolton Institute. And here the model has got a 28 Hertz mode, and in modern terms quite a low torsional stiffness of about 12 kilonewton per degree. And what we want to do is to really increase that performance with the minimal amount of mass increase. So how do we go about doing that? There's a lot of complex parts in here, so it's how do we address that and identify the bits to put our efforts, where to put our design engineering efforts into. So what we do with RDM is you very simply get the tool to create you a design space automatically over the existing structure, and there's different ways it can do that, but it's a few clicks and it's created that additional material over the structure, connecting it to the structure, ready to go. Having done that, it's then submitted to the optimizer. In this particular example, it was done in Genesis, but the process is also available in the SimCenter environment as well. And so what it's doing is it's removing almost all of that design space you just created, leaving just a small amount. So in this particular example, I think we're looking at around about 3% of all the elements that we just created remaining, and we get these blobs of material. So maybe you're now seeing why we started to call it magic custard. The yellow, very much fitted. Okay. So what do we do with that result? Because that's the key thing. And again, it's important. What I really want to get across this evening is that optimization should not be separate to conventional iterative design and the designer's work and the engineer's thinking, but it's additive to it, and it really gives that extra bit of guidance along with already good brains. So how do we interpret? So first of all, if you can stick to just nice simple joining changes, all the better. So you might want to make a change to spot welds, your SPRs, or adhesive placement. In fact, there are specific processes to optimize adhesive placement already. We'll cover that today, but again, it's there. The benefits really are no or negligible added mass. Second way we can interpret that RDM result on a body in white level is to redevelop geometry in the area. So what we learned over the years is a lot of people, well, when you design a body in white, it's not one person drawing a whole body in white. There are dozens. You know, somebody doing the front subframe, somebody doing the sills, somebody doing the roof, B-pillar, and they all design their part. And it's often the problems when that whole design is released and somebody assesses it, or a team assesses it, it's the connections between, the assumptions between those sub-parts of the body in white are where you get problems. So the RDM identifies that and gives you that sort of area to focus on and allows you to just rework the geometry in many cases. So if that's the case, minimal or no mass increase and no real change to your process. And then lastly, sometimes with the RDM, because it is creating material above and beyond your existing part, is it can create you new load paths, and it may yield something that says, do you know what, I need an extra part there, and that's going to give me a big improvement in what I've got. So they're sort of the steps in terms of complexity and cost as we go. So we take a little look at that. So going back to our image, what we've achieved in this particular case study. First of all, the smaller little lumps. You can see there was a tiny little blob there inside the sill, some at the front here, and some up in the header rail. And with those, we just simply added 10 more spot welds and increased the stiffness by 1%. No mass change, nice and simple. So that's a really easy win in terms of a change. And again, it's just pointing in that direction to go. Next one is looking at geometry updates. So if I just play this, all being well, yeah, it does work. I always test the videos. So if we take a little look around at the back of the car, what becomes very clear, and again, combining with people who have got good experienced brains in automotive will also tell you is for a hatchback, it's that tailgate that is key in terms of torsional stiffness. It's a big opening. So here it's showing you fundamentally what to do, and saying I need to get some extra load path, I need to connect from here to here and manage it. So what we did is we actually looked at the deformations in the area. Now it highlighted it and said, yeah, okay, for a small change, which is actually 60 grams, so not a lot, there was a 3.7 hertz or 13% increase in the first torsion mode. So just reworking that geometry based upon what it was telling you was key. And then that was taken a little further, so the lower part was reworked as well. That did increase the mass. There were some changes there, but say 0.7% increase in mass, and it gave a 12% increase in the first mode. So you can see just reworking that geometry where it's telling us to is really a key benefit. And lastly, this is where it was quite interesting because we did this work, I'll show you in a moment, prior to knowing anything else about the evolution of the design by Ford. So if we take a little look at where we added a new component, what became quite clear, if you zoom in the back, is this lump of RDM material was also connecting from the tailgate aperture just below the lights back to the wheelhouse. Really clear load path. It connected that area there, and so we added a part. Just a simple press part was added in to connect between, and that gave a really big increase in the stiffness. So yep, so 1.2 kilos for the part for both sides, and it gave a 6.5 hertz increase. So really big increase in the improvement. And this is the bit that was really interesting. So we looked at that and we noticed that this was the body in white for the 2002 Fiesta, and then I promise scouts on it and all those things. But after the event, we then learned more. It was about a year later we learned about the 2008 Fiesta, whereby they had in fact included a part there that connects between those parts. So that was good to see it pointed in that direction for what we had. So just to summarize on this, I think I'm doing about right on time as well, hopefully. We've gone from 28 hertz to 40 hertz, really big increase. Torsion's gone from 12 to 20. There is a 7.5 kilo increase. So that's, doesn't sound like optimization when we've added mass, but hopefully you understand that it is very efficiently added mass in the right places. Sometimes you've got to add mass to get the performance you need. And this was really a 2-day study to see what could be achieved. But just to slightly expand on the tools that are available in optimization, what do we do with that? Is there any, can we get some of that mass back? What else can we do? So just to summarize lightly here, so then a gauge optimization was done. So gauge meaning the panel thickness. What we did is to not become too controversial. Anything in grey was not changed. Anything in red was increased only, so crash structures and things we weren't messing around with. And then blue was increased or decreased. So what should we do with those areas? Here we see the change. So it's a bit of a colour plot to absorb in a short webinar, but certainly it's something that you can see where it's moved the material around. And here we can see it's very easy to get back to, in fact, below our initial weight, whilst we're still maintaining our same 40 hertz target and 20 for the torsional stiffness. So that's Nice and straightforward. So what else can you use this process for? What else is it used for? I think this was first introduced probably around about 8 years ago as a process. We've used it, and our customers have used it an awful lot ever since. So you can see here for this is a clutch housing, the philosophy of a minimum design envelope starting from topology, and then each of these iterations is where the RDM has been used to guide reinforcement. Some reinforcement has been added by the designer, it's been reassessed, and then a bit more RDM says, well, you're almost at target, but not quite, you need a bit more. So that's these extra red bits. So you see extra ribs added, and you get your solution. You can see it's been used here by Jaguar Land Rover in some of their architectures to look at improvements. And that's a good example of a poor condition that has come through the natural cycle of developing a body in white. So one person designs one bit, another does another, and there's that disconnect. So it's highlighting that and saying, there it is. I can see exactly why I need to focus on that area. And then the customer here, Pens, have been using it for looking at concept schemes to reinforce body white architectures. So it works for that. It also works on trim parts. It can create shell rib structures as candidates. It's just a really flexible tool, and that's a real objective of ours, is to get those tools used so that optimization is used more daily. Okay, I've just seen a brilliant question come up. It really is a fantastic question because it's something I wanted to get done for a long time in one of my requests. I shall answer it. Okay, so just to summarize, because it's 42 minutes past 6, so I need to get on. The advantages of optimization-driven design. Why should we do it? What can we do? So I've kind of gone through these points already, actually, very early on. But we can look at identifying best designs and meeting those multiple requirements. And meeting multiple requirements is often the real key. We can resolve design issues throughout the development cycle, and that's the bit. It's really important in optimization to just get confident with it. If you don't, then you can get into trouble very quickly. You get discouraged because you don't get what you want, and you go back to just iterating. If you invest that time in optimization, that's kind of what we want to do as a team at GRM, is to get you on that learning cycle. Then once you've embraced it and you know when to use it, when it's maybe biting off more than you can chew, that's where you get the real strength from it. It saves you time. It doesn't always save you time, depending on what you've got to do to set it up, but certainly it can do at the right occasion. And then lastly, you can really explore and understand your design in a design's performance. See what is done. So why optimize? I am extremely biased, having spent 20 odd years doing optimization, but I don't know why you wouldn't. It's as simple as that. It gives you information you can't otherwise get. But just to caveat that, why wouldn't you always use it at the right occasion? Sometimes it isn't the right occasion, so mix it in with your day-to-day engineering. Okay, thank you very much. That is my talk done. There are a few questions to go through. I think, Ryan, you're going to rejoin and quiz me to see what trouble I can cause.
Well, first of all, I'd like to thank you very much for that really engaging talk. It was great to get your insights and learn from your knowledge and see some of the real examples of how the work is applied. So thank you very much.
No problem. It's a real pleasure, real pleasure.
So we'll get to the questions. First, what are some of the common errors made when using simulation to optimize?
There's quite a few there when we do that. The key thing is believing in simulation, because if your simulation is a load of rubbish, your optimization is most definitely going to be a load of rubbish. So having confidence in the base simulation you're working with. And the kind of things that often go wrong, if it's something like a structural problem, then the boundary conditions that you consider may be valid for the particular design you've got. But if you're going to do an optimization that's changing the design, your assumptions may not be valid, and they can often dictate the solution that you get. So making sure you have that fundamental grasp of what you're simulating is important when you consider what optimization is doing. It's doing what you would do manually. So if you changed it yourself and it gave you rubbish, well, the optimizer will give you the same thing. Another last thing to point is people sometimes ask optimization to achieve totally infeasible designs without thinking about whether they could achieve it themselves anyway. So, and they get frustrated when the optimizer can't fix the problem, but they couldn't themselves. So it's just keeping in mind practical application, I think, is key.
Yeah, that's a really interesting point, actually, because a point I was wondering was at what stage does design for manufacture play a part? Because, like you say, if your optimization suggests a design that can't actually be made, what happens then, or is that a case of what your boundary conditions are set to?
Well, for the different applications, so we fall back to structural because it's easy to see and understand. That's where I always advise to try and advise it with what you're doing as a development anyway. So when you do topology, there are many ways you can look at manufacturing constraints. So you can put casting constraints or extrusion constraints, but they still don't give you truly a design that you're ever going to make. There are lots of processes that you need to consider on top of that. So if you can do something like the RDM, and it's not just the RDM, other processes apply, but whereby you're designing it, so you get a concept from topology, you design something that then is taking a lot of those manufacturing factors in place, all the design for manufacture, and then you add on a bit of optimization as you go, and you bring the two along the journey together. I don't know why I'm waving my hands in front of me because my camera's off, but I know what I'm doing with my hands. Yeah, then you end up converging on that solution that is manufacturable at the end by making sure you're bringing both streams along in parallel.
Excellent. So our next question, do you feel the adoption of optimized design will affect current industry standards for factors of safety in structural design?
Oh, that's a good deep question. I like that. Yes, so I mean our general rule of thumb on any optimization is similar to what we do in the structural design. So typically what we look for in our simulations, it's rule of thumb, it's not a scientific answer, but it's about 80% of performance. So if we have a factor of safety, so we're up to 80% of our structural requirements in a simulation. Well, optimization is just iterating that simulation. So the same rule applies in terms of the factor of safety we consider. The end solution of the optimization is a simulation. So we follow the same guidance that the structural design and the simulation would also apply to. There are developing methods in some of the tools that we provide, and again, others can do it too. When you're doing something like the gauge optimization or the casting thickness optimization, you can introduce reliability analysis in there. So you can look at variations in manufacturing tolerances in the optimization, and considering that factor is quite important as well. So you get not, rather than just pure optimal solution, but you get something that's a little bit more robust. Again, it becomes more complex, but these factors, as the process becomes more and more understood, get added in. Okay.
Excellent. And we actually mentioned about this a bit before the webinar, but we've got another question. Do you know if any of these optimizations methods could be applied to battery technologies?
Yes, simply. I mean, the key thing, if we look at the DOE and the response surface methods, they can be applied to absolutely anything. If you're simulating something, and if at any point you've sat there and you've done a simulation and you've changed a parameter, a dimension, or a flow velocity, or something you've changed 2 or 3 of those, and you'll simulate it again to see how it changes the performance. Well, at that point, that's where design of experiments, response surfaces, and there's other methods, expand a bit more on those I covered today, can allow you to understand those changes, and ultimately, once you've got that understanding, the optimization is a natural sort of byproduct of that response surface methodology. So yeah, absolutely it can be. We've done it on a few different aspects already for battery technology. So yes, I know it can be done.
Excellent. Our next question, the RDM looks very useful technique for body and white optimization. How are the volumes of RDM ranked in effectiveness to target panel changes or new parts?
Yeah, that was the question. I saw it pop up, and I thought, I know that man, and I know that question. It's a really good question. And it's something we do sort of manually ourselves from the solution. So each little blob, as it were, that sits in there, we just perform a direct sensitivity analysis of each of those blobs. We put them into different properties and perform that sensitivity analysis and identify which one is the most important. We haven't quite automated that as we want to as yet, but it's something that we'd like to do. So typically, you tend to just have to go and look at it and see what the densities are in the area, and sometimes just take the parts out and stick them in yourself and see. But we've got little scripts that do it, but it's something that I think is important to be made a bit more elegant. But it's part of the joy of writing software and technology is it never stops.
Great.
Okay.
Our next question, do you optimize for materials with non-homogeneous properties, for example, rolled metals or directionally layered composites? Also, how have your processes changed for additive manufacturing?
Okay, cool. Yes, yes, and yes is the whole thing about that. Where is that? I can't see that question on the list, if I can remind myself of it. But yes, so composites, first of all, is something that we have been optimizing for many years, and we have some really powerful and unique processes for optimizing the ply shapes of long fiber composites and their placement, and that is a really mature process to do. In terms of more orthotropic materials, so some of the things I've encountered is in additive manufacturing where you think the material is isotropic, but it's not. It's orthotropic on the build plane, and so the topology methods are quite, it's quite possible to just simply define an orthotropic material and optimize the topology and layout for those properties. So that can be done. In terms of how the processes have changed through the advent of additive manufacturing, they've changed a little, but not a lot. It's a funny thing. Topology has been around, and what we're calling generative design, although there are extensions to topology beyond that in generative design. That whole discipline has been around for well over 20 years, and there are a lot of people using it and have used it for that time. But it's really found its home, I think, with additive manufacturing, because you've had to bypass the need to interpret that crazy topology shape into something real. You can just essentially manufacture it close to as is. But there are limitations. Again, in even additive manufacturing is not this magical process that you can just make what you want. There are overhang constraints and so on, and so the evolution of the tools are to introduce some of the manufacturing constraints that additive manufacturing brings. So you already had casting constraints, extrusion constraints, now you have overhang constraints, and so on. But I think that still has some area to develop. Okay.
Great. When establishing torsional stiffness, is the twisting torque applied to the vehicle via the suspension mountings because the stiffness of the body outboard of these points is not relevant?
Then establishing torsional stiffness is the twisting torque applied to the vehicle via suspension mountings. Yeah, so in this particular example, it's a rig that is looking at the turret tops, both front and rear, and applying like the real physical. Again, I'm holding my hands up. You can't see that my camera's off. There's a rig essentially putting that load in, so a torque is applied at the center line, and then that's transferred into upward and downward moment, that upward downward force on the turret tops. So yeah, and again, that's the key thing. That's delving slightly into the simulation of the process rather than the optimization. So if you get that wrong, your optimization is wrong. So it's a good and relevant question to highlight that importance of asking the right questions.
Yeah, absolutely. Our next question, are there rules for which system, gradient or DOE, to use?
Oh, that's a good one. I like that. There aren't formal rules. It tends to be what is available. Gradient based, if you want to get to an optimum answer, then and there is an available technology for it. So be it structural, internal flow simulation. I think in terms of MATLAB type simulations, there's often, if you can calculate the gradients, there are optimizers in there that are gradient based. So if it's there, it's fast, and it gets you to an optimum solution very, very quickly, and that is key and gives you huge design variability. DOE, you're using, if there isn't a precedent of getting those sensitivities out of gradients, but you just want to apply optimization to your process, and that's where it becomes very powerful. So yeah, I think that's where you'd fit with the different disciplines.
Fantastic. So I'm going to take 3 more questions. The first, what's a simple and intuitive platform to start optimizing on as a beginner?
So there's a few things. The University TU Delft over in the Netherlands, if you go to their website, there's some free, there's even a phone app called Topopt you can get in your iPhone, and you can start playing around with topology, putting loads into seeing how topology works. If you're a student working in the whole world of SolidWorks, there is a free version of our SolidWorks tool. It just works for one load case. You can download it off our website and play around with it. And it's fairly comprehensive. We've done a terrible job as a company of tracking who downloads it. We don't know, but we just know that when somebody creates a user account, we assume they've had a little look at what's going on. So
yeah, that's great. Our next question, how do you create the design volume for RDM when adding material? Do you create elements based off the FE mesh size that is already within the model?
So there are a few tools available in the RDM application. Essentially, the whole point is it's FE-based creation of elements, and they're done on the fly. So there's something called block search, where basically it's just going over your part with a few parameters. So I found some existing part and I blob some design space on top. There's a control parameter for that. There's also a projection method whereby you can basically, it'll just fill material between, you look down a particular direction and look at the extremes in top and bottom of that direction of where the mesh exists. It will fill between it, and then there's wrap and volume fill as well. So they're there, and then once you've got that, you can then just pull and drag and chop that design space in and around your existing model without fear of deleting your existing model as you go through it. So it's quite flexible to then just add that material. As I say, you can create it as solids, as we went through with the body in white application. But if you're doing something like an instrument panel or a door case or a casting, then you can simply tell it to create ribs in a shell mesh format within the part of a certain direction, pitch, and thickness, and you can design the thickness of those ribs at the same time as whether you want them. So it's quite flexible in that approach.
Fantastic. So our last question, how do you get around the issue of local or global optimum solutions for gradient-based methods?
Oh, I like this. That's somebody who knows these things. So there's a process we've got in our tools, and again, I can only speak for our tools. So we have something called multi-run, and this is bringing a little bit of DOE into gradient base. So for those listening that aren't sure what we're talking about here, if you go back to my graph, I go back to, I'm gonna hop back. We've got this the last question, so we can take the time to do it. Thanks, Rowan, for your patience already. There we go. So if we look at this graph, the way it works is that's very nice, and we've got ourselves to this trough in here. But if you're only moving small amounts at a time and you started here, then the optimizer might chug along down this line and get to this little trough and go, yay, I've won, I've got the best solution. But actually the better solution is down here that we found. So this is called a local optima. So generally, as the rule goes, if you're looking at stiffness of structures, and this is general, not specific to everything, then things that get thicker get stiffer, things that get thinner get weaker. So you kind of are not so prone to local optima, although it is possible. When you have something like composite optimization, where you apply orientations, you look at the angles of those fibers, you're really prone to local optima because you can go stiff, soft in a little wavy line with the angles, and when you combine many plies, it's very prone. So what we do, I did have a slide of this once that explained it, is we use a design of experiments Latin hypercube to start multiple gradient-based solutions. So we do it all in Solve, it's all managed with inside the code. But we'll start at this position, we'll start at this position, and typically we'll start around about 10 different positions, and internally it will solve the gradient solution 10 times, and it will monitor the best solution and say, there we go, that's the best one. It doesn't guarantee you're at the global, but it certainly gives a very, very better and stronger chance of doing so. Okay.
Excellent. Thank you very much, everyone, for attending and for the great questions that we've had. This webinar will be available on the IMechE YouTube channel in the next few days. So if you want to revisit what we've gone through tonight, you'll be able to find it there. Thank you very much for attending. Take care and hope to see you soon for physical events and virtual events in the hopefully not too distant future.
Indeed. Thank you all. Really appreciate you attending. Take care.